All right, let's just jump right in. Welcome to the Explainer, everyone. Today, we're diving into the surprisingly beautiful, highly predictable, and honestly, almost elegant magic that happens behind the scenes of electrical circuits. Specifically, we're focusing on resistive circuits, getting into the nitty-gritty of voltage and current division.
To really kick things off, let's think about a real-world, high-stakes question. Imagine you've got a standard 9-volt battery. How exactly does that single power source safely run both a super delicate microchip and a power-hungry LED without instantly blowing that tiny chip to pieces? I mean, if you feed 9 volts directly into a component rated for only 3 volts, well, you're going to let the magic smoke out of your electronics. The secret to solving this puzzle lies entirely in the incredible utility of voltage and current dividers.
So here's our quick roadmap for today. First, we'll hit Kirchhoff's laws. Second, measuring circuits. Third, voltage division. Fourth, current division. And finally, some real-world applications. Starting off with Section 1, Kirchhoff's basic circuit laws.
Before we can even touch the math with dividers, we have to respect the physical laws that govern how electricity actually behaves in a closed space. This brings us right to Kirchhoff's current law, or KCL. I want you to imagine a node in the circuit, like a perfectly balanced, super busy traffic intersection. In a closed system, you can't just spawn new cars out of thin air, and cars can't just mysteriously disappear. Whatever flows into the intersection absolutely must flow out. The total inward current perfectly balances the outward flow, meaning the sum is exactly zero. And you know, this pairs perfectly with Kirchhoff's voltage law, or KVL. If KCL is about the traffic, KVL is all about the energy of the journey itself. KVL states that the algebraic sum of the voltages around any closed path is zero. If you trace a closed loop through your circuit, the energy provided by your battery is completely dropped or used up across your components. It delightfully zeroes out by the time you get back, perfectly satisfying the laws of physics.
Moving right along to Section 2, measuring voltage and current.
Okay, so we know these invisible forces are governed by these incredibly strict rules, but how do we actually observe them? How do we measure them without accidentally breaking our KCL and KVL rules? Well, this brilliantly illustrates the concept of ideal meters. An ideal meter has absolutely zero effect on the circuit it's measuring. It's basically a ghost. But to be a ghost, the tool has to completely adapt to the circuit. For current, we use an ammeter. Because it measures flow, we place it in series, literally right in the path of the traffic. To avoid slowing that traffic down, an ideal ammeter has to have 0 ohms of resistance. Now for voltage, we use a voltmeter. We place it in parallel to measure the energy drop. To ensure no current accidentally detours into our meter and messes up our intersection, an ideal voltmeter requires infinite resistance. The measuring tool fundamentally shapes itself to the physics.
All right, Section 3, series circuits and voltage division.
The crucial point here is that the rules of current and voltage literally dictate how circuits are built. Let's look at the first of our 2 mirror image core concepts. When you connect components head to tail, they're in series. Because there is absolutely nowhere else for the electricity to go, these components are forced to share the exact same current. But remember our KVL rule? The voltages have to drop to 0 across the loop. Because the current is trapped on this single one-lane road, it's the voltage that has to do the splitting. A series circuit natively acts as a voltage divider.
Which leads us to a massive aha moment, the voltage divider formula. With just 2 resistors, you can take a dangerously large input voltage and chop it down to exactly the output voltage you need. The rule here is wonderfully simple. Because the current is constant, the bigger resistor mathematically demands a bigger slice of the voltage pie to push that current through. The voltage division rule basically says the voltage across any series component is a direct proportional relationship. It's the specific resistance times the total supply divided by the total resistance of the circuit. It's clean, it's proportional, and it just works.
Flipping over to Section 4, parallel circuits and current division.
Let's completely flip the script and step through the looking glass here. If series circuits divide voltage, what divides current? Parallel circuits. In a parallel setup, components are connected across the exact same 2 nodes. Because they're pinned to the exact same spots, the voltage drop across them is identical. So the total circuit current divides itself into the parallel branches. Now the really fascinating takeaway is what happens to the resistance. Connecting resistors in parallel actually makes the total equivalent resistance smaller, always. You are literally giving the current alternate parallel paths to flow through, which eases the overall bottleneck. And here's the rule for calculating exactly how that flow splits. Take a really close look at the math for a second. Did you catch the trick? The opposite branch resistance is sitting right there in the numerator. Why? Well, because current cleverly prefers the path of least resistance. It distributes itself inversely to the impedance to minimize the total energy expended in the whole system.
Let's actually put these mirror concepts side by side because it's genuinely fascinating. A series circuit divides voltage, perfectly satisfying Kirchhoff's voltage law by adding resistance directly. A parallel circuit divides current, minimizing the total energy expended by decreasing the overall resistance, creating an inverse relationship. Once you see this beautiful symmetry in circuit design, you really can't unsee it.
Finally, Section 5, Real-World Circuit Applications. Now, we know the rules, we know how to measure them, and we know the math. Let's see how this actually builds our modern world. Because this isn't just dry textbook theory, it's the fundamental operating logic of every device you own. Remember that delicate microchip we talked about at the very beginning? Engineers use these exact division principles to protect it. Voltage dividers are everywhere in what's called signal conditioning. They step down large, dangerous input voltages to safe, readable levels for sensors. They're also absolutely essential for biasing, which is just a fancy way of saying setting the correct operating voltage point for things like amplifiers to wake up and function properly. By picking the exact right pair of resistors, engineers can essentially dial in a custom, perfectly tailored voltage from a much larger supply.
To wrap things up today, I want to leave you with a slightly broader thought. We just learned that in a current divider, the flow naturally splits precisely in a way that minimizes the total energy used, inherently favoring the path of least resistance. It's a mathematical certainty in electronics. But where else in nature do we see this exact same path of least resistance at play? Think about how river systems carve through a valley, or how tree branches grow, or even the jagged path of a lightning strike. The rules that govern a tiny little circuit board are the very same rules echoing throughout the entire natural universe. Keep that in mind next time you power on your phone. Thanks for joining me on this explainer, and keep questioning how the world is wired.